Good morning, Raymond.
Good morning, everybody.
Hello, everyone.
Good morning.
Hello, hello.
Okay. Glad I can hear you. That helps a lot. I thought I have a microphone problem. Um, so today is July 3rd, which is a day before the holiday for US part. And I would I think probably a lot of people is already in the holiday mood. So thank you for joining us today. And how can we get how can we get a whiteboard here? Oh, let's share. Okay, great. All right, so before before we go into the outlines, I have one interesting thought that I think I can share in here. And the and I bet probably maybe some of you already think of this before. So let me go over this part. Oh wait, it's not here. All right, so this, for example, this is uh the SUE the SUE connection diagram in here. So you see, when you see the switch connection, for example, this one in here, it says the XPU 0, XPU 1, XPU 2, blah blah blah, all the way to XPU 63, something like that, and then you have so many different switches and similar things that when you're looking at the UA link, they're talking about something like this as a structure, a network structure, like you have the UA link switch, and you have so many um, accelerator in here. And I start kind of drawing the network topology by myself, and this is what I found. So let me quickly draw one, and hope you can uh, you can follow my thoughts. Oh, so we can discuss if this is totally makes sense. Um, so let's say if you have if you have something like a accelerator car, a accelerator in here, do they have a better shape? Oh, okay. They have a better shape in here. So let's say if you have a one accelerator, um, and and then you have uh, another accelerator. Oh, well, this feels bad. Um, Sorry guys, I should have drawn probably a better find a better way to draw it. So my thinking is, let's say if each accelerator has 1.6 uh, t by of let's say not 1.6 t by, let's say just 1 terabyte of uh, hardware, and each one of them is 200 G. So that means you total have so it's 40 lanes uh, for each accelerator. And so that means let's say if you have uh, accelerator, each of them will have 40 of little uh, lane, but you likely not gonna have 40 little lanes over here. You're probably gonna have something like uh, by 8 or by 16, right? So some of them has to be grouped together, some of them has to be grouped together. Um, and and the things is you will have a rack. However, um, so let's say if you have a switch in here, each of the switch has let's say each of switch has 256 uh, port in here. So that means you can have 250 that means 256 of accelerator. And because of each of them has 40 lanes, so that means you need like 40 switches to connect all of them. Um, so so what you end up with is actually a very simple things. Because of rack, um, right now you probably have like 100 kilowatts of power limitation. That means you can only put somewhere around maybe 32 accelerator in a system, right? Because let's say you're not only have the accelerator, but also the CPU, RAM, re, re um, storage, power, 70 or 80% of power conversion efficiency. So fans, coolings, additional things. So that means if one of the accelerator will end up with somewhere around 600 or 800 watts, right? So that totally makes sense. For 100 kilowatts rack, you probably only want to put 32 accelerator inside, and now you want to connect something like a 256. So if the switch is one of the switch is in the center, then um, you will only have 32 that can probably live with copper, and the rest of the connection, uh, has to be many rack because only 32 in here, 256. That means you need an A rack uh, of the computing rack. And plus you have to put 40 of these switch. So that means, you probably end up with something like a switch rack at the center. So that then your connection from the switch to each accelerator will end up be the same distance. So the latency can be similar. Um, and because you have to cross a rack for maybe 4 racks, then you end up have to be at least 10 meter, able to travel 10 meter to 20 or 30 meter. That's probably could easily be like that. So it's pretty much put the electrical cable out of the equation. It has to be optics, unless you don't want to connect it something like a 256. All you want to connect is a 32. Then you can do is electrical. If you want to do something like optical, but if you want to do connecting something more than 20, 32 accelerator, or you were pushing to extreme like NVIDIA 72 that the scale up network connected to 72 use everything liquid coolings and put 500 kilowatts into a rack. You cannot, you have to go into optics. So that's what I think, when we can put it into the white paper explaining, like in the scale up network, you probably really need that. I don't know what you guys thinking about this.
I think this is pretty obvious, right?
Yeah.
Um, Actually, NVIDIA started earlier with H series, and they really started something called I think NVL 256, actually with optics. But then they backtracked and started to get back to NVL 72. But so this is actually pretty much uh, people implement it if they want to do optics, or they want to build more than one rack, I think. The best they
Right.
can do, maybe 2 racks with ACC or AEC. But I think more than 2 racks, we probably need to do optics. No, I think this is right to construct visuals.
Yeah. And one additional things that I've been thinking of is, if let's say if you have a port going into here, right? And then you have another port one to going into another switch. But for example, our pluggable or something is always something like a by 16 or by 4, by 16 by A, right? Um, and if you have to, like, one LAN you have to create a plug for like a one LAN to one LAN, it is really not that efficient. So that's what I'm thinking is all these things in between. Um, there's one things I think we're missing in our optical connection is we might need to have a shuffle in between to group all these fibers, and then able to plug it in these things and plug it in here fairly easily. So um, so I don't I never get in touch with Shuffle before. So you guys probably better have an idea, a better idea about that thing. So I'm wondering if this observation is correct.
Yeah, people actually do, they call it shuffle box. They
Uh-huh.
actually have a box to coordinate where to go where. So from transceiver point of view, it's fully parallel. So you can actually group transceiver output to whatever destination you want. So these are the breakouts already being deployed pretty widely.
I see.
So basically, if you're looking at a transceiver, for example, 8 lane or 16 lane, they can be grouped whatever you like to break out. For example, you can use 2 lane per port, or you can use 4 lane per port,
Right.
right? Depends on how you do it. Like NVIDIA, they basically, I think NVLink is 400 gig. So you basically have 200 gig into one destination.
Mm-hmm.
So not
I see.
necessarily, yeah, a physical lane mapping to logical lanes. You can actually group
Mm-hmm.
however many physical lane you need as a right granularity for you.
Got it. Got it. Yeah, and I think that would be the unique things for optics, right? Because the copper, um, the copper, especially all these twin X, it's hard um, to get additional connector in between, and then without adding significant amount of loss to that.
Yeah, no, it's clearly is the motivation to deploy optics.
Great. So I'm just sharing my thoughts in here, and let me switch back to the new.
If you want physical visuals, I don't know, you noticed there's a Huawei recent announcement about Cloud Matrix. They actually deploy 384 GPUs with optics, actually with LPO.
Yeah,
You can actually see the physical construct that.
yeah, I saw that things, but they one things that I don't think I mentioned, maybe I missed it in their paper, is the shovel part, and and I think uh their configuration is a little bit interesting, because I think there are like 2 layers of the switch. They have 1 layer of switch internally in the box, and then the um, the second layer of switch to connecting between rack to rack. So it is slightly different than what Scale Up Network or UA Link does. Because when I'm looking at their paper, there's a 2-layer switch, so there you can have some reduction, and that would make the make some of the chaos for the connection go away. But as you can see, their latency, I think their round trip latency is it's always like 2 microseconds or more. But in the SUE and UA Link, they only use 1 layer of switch. They have the limit for the latency somewhere around 1 microseconds. But I got inspired by the cloud metrics, Huawei's cloud metrics, to actually just draw the things, and that's how I start feeling like, oh, 1 layer of switch. Yeah, it is possible, but it is when you're going a little bit more than 32 accelerator, you actually have to use optics in order to implement it, and you probably need these shuffles to make the wires more organized.
Yeah, so I think it's up to the radix, right? If you have lots of ports, then you can use just flat 1 layer switching. Actually, in case of NVIDIA, they basically have actually NV switch seems to have limited port counts. NVIDIA construct a NVL 576. I don't know if you're aware of it. It's actually 2 layer switching, but they never deployed it because it's like so complex of 2 layer. So they only deploy one layer switch.
Uh-huh. Yeah, I think I'm gonna chase that. I haven't studied it yet. Okay, let me switch to my screen. Here, we have, so I made a slightly edit to the outline. Um, Cooling is copper. You can still go to. That's an interesting thought. 500 rack was liquid. I think this is the things that, you know, one of the comparisons that it's interesting to um to compare that the 100 kilowatts rack with optical link compared with a 500 kilowatt with liquid cooling. I think I wonder if anyone would have the some of the insight, or people could get a rule of thumb numbers for the cost compared with air coolings and liquid cooling. And because we're pretty much familiar with what copper's cost and the optical network costs, at least in this group. And you know that can sort of convert it to the ROI, right? So for example, the cost of tokens in here, that's what we hopefully able to help analyzing in this white paper, give people the suggestions that how the things can optical can help, if optical can help, or if optical can stimulate a different idea that using optics does not increasing the cost, but you know, comparable with using copper. So I think that's exactly what we like to see in the discussion. So I sort of consolidate the two outline into a new one, and I hope everyone will be able to review. I just come out with a new file, and I'll share with this to everyone. And feel free to edit, give comments, or you can sign up any topics. Please sign up to any topics that you think you can contribute. So like the last time we discussed, the majority of the outline will follow the alternative outline from 0.1. So as you can see, it is come out with like a introduction of scale up network and the unique challenging for that. So there are some of the detailed thoughts, and I'm glad people's already signed it up. And then we going into the optical link advantage and disadvantage. So some analyzing about how optics can be implemented in the scaled up network. And there's what would be the disadvantage for that, because the optical reliability or the cost is slightly higher than the copper cable, something like that. And then in order to measure that, we going into the key metrics, right? So so these are the key metrics. I kind of put all together in the uh, in the in put all together from two outlines in one. So um, so the cost, the energy part, and can be measured by the picojoules per bit, or maybe operations per watts, radix reach, all the things, and then different configuration, the architectures for the optics, with retime, non-retimes, or just single side retime, different form factors, with different electrical interface, different optical interface, and then what would be the impact for that? And there's one additional things. I think these two are supposed to swap. Um, I should do that. Um, with different kind of fiber, is there some more mature fiber, the single mole, multi mole, something like that, and uh, in the hollow cores, or anything that could further exhaust reduce the latency. And then I add one additional sessions in here. I think there's some unique challenge if you want to implement the optical scaled up interface. For example, how the sideband is supposed to go, the receiver detections, that the copper, it's probably easier to do so. Interoperability, that
Sorry,
how
Bobby, why are you specifically talking about sideband if looking at the mainstream scale up protocols already not using sideband, that's only unique to PCIe, right?
Yeah, that's a good point. That's a good point. Because I think some part of my mind is still stuck at PCIe, especially I just recently go over the UA Link 128 spec sheet, and that kind of put it, stuck in my head to when I compose these things. That's a good one. Oh, one, two. Talk about this if 200G does not require. Um, yeah, that's a good one. Um, thanks for pointing it out. And interoperability, if the from different vendor or switching, switch company could use a different connector or something like that. And
What do you mean receiver detection?
um, so so I think that's also something that stuck in my head for the PCIe, because the PCIe protocol has a receiver
Oh yeah.
detection,
Okay. Yeah,
and
very
and
specific to PCIe, right?
yeah, and I'm one things I don't exactly understand um, how the Ethernet part working is, when you plug it in the connector, and how maybe it's built in the protocol already that
Yeah,
it will
exactly. They have an
continuously.
auto negotiation. So
Yeah,
yeah, we don't, yeah. So Ethernet is pretty simple. I mean, it's no sideband, it's no
right, right,
specific,
right.
but there is a time needed to set the link up.
Uh-huh.
But it's all in band, right? So there's no
Yeah, yeah.
additional.
Right, right.
Yeah, Ethernet is very optical friendly, so I don't need a lot of extra things. to make it work.
Right. Yeah. And so so maybe we should skip that part. I don't know if this is this Rini because it was just like, something stuck in my head and when I work on it, working on the outline, I just kind of type it down. Um in 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 the um
Yeah, I would suggest take these parts out unless we specifically want to talk about a few different options. And then when you talk about PCIe, you can talk about this part, but it's not a main part of the discussion, right?
Okay. Yeah, I think I can I'll move that. I'll kind of just cross it out in here. So where, where is it cross?
But you probably will talk about the options of scale up, for example. Then you can maybe in those subsections, you can talk about this if you list PCIe as one of the options.
Yeah, so I might that's what I'm trying to just maybe just cross it out instead of completely delete so that so I would forget. Um and okay, and the next thing so it would be the network management. Um the um I think it's probably be be well established at some point. I don't uh I don't exactly familiar with this part, but I think this one would be the one that we can maybe let more network architect people to thinking about. Is all these things, is there a specific things that uh the the how the optical when optical failure uh happens, what can be detected, how to managing that, that can be uh, slightly discussed in here. And the very last sessions, I think we showed that before is what are other
So Bobby, on the challenge side, I think, people all talk about these things, but maybe we can put in the session is the power and reliability. These are the typical people ding on the optics, right? Like, are you consuming too much power? At the end of the day, it's not zero power, but it's really like compare relatively to, say, GPU power. You don't want your optics interface to burn like a big portion of GPU power. So that's kind of one thing I think use it to highlight, what later on optical technology relevant to address these challenges, right?
Yeah. Okay.
And you probably can list reliability as separate bullet because power and
Mm.
reliability, they are not really the same. But reliability is important. So that also pointing to what technology relevant to address the reliability, right?
Uh-huh.
Yeah, Bobby, I could say a little bit about the network diagnostic section you've got there.
Oh, okay.
So
That's
this is related to the hyperscaler's request that if something goes wrong, if they can pinpoint where the problem is. One
yeah,
of the complaints I've had is if you use a non-retimed module, then there's
right,
typically no diagnostics in it, so you can't
right.
tell which end of the link needs to be replaced. That's
Mm-hmm.
really that's really that's really what this I believe this section is meant to be talking about is, you know, how do you deal with that if you're trying to achieve lower power?
Uh-huh.
Yeah, they're all related.
Yeah. Fantastic. I think that's a very um very important, the education part for this white paper. In the last sessions, I think it will be, I think this is more like, I'll ask if other teams like to join in for a little bit to maybe share some other works in the OCP part if they are already looking into it. And also some more future things like optical switch stuff. It doesn't list up in the scale up network, but could be in the future that optics can change the network.
Actually, Google already deployed it. There's a lot of interest on OCS. If you really want to talk about it, you may want to list as a separate section because this is actually already lots of discussion on using optical switching, and because Google already deployed it for many generations.
Ryan, that isn't scale up, is it? That's more of a scale out connection, I believe. Is that right?
That's not true. They started out with just general networking in a aggregation top layer, but if you're looking at their latest few generations, they basically using this torus structure in rack. They all use copper, but the minute you go out of rack, it's actually go to OCS. So you basically can tie together multiple rack into a big cluster.
What I meant by scale up is I don't think it's a memory consistent domain when you go through the OCS, like you would have with UA link if you tied a bunch of things together. At least that was my understanding.
Yeah, if you look at a topology, I would say that's really equivalent to scale up because they don't really put it this way. If you're looking at individual TPU, so to speak, they always reserve certain portion go out of rack, like 1/3 of the bandwidth going out, 2/3 of the bandwidth in rack.
Yeah. No,
So
I
from
agree.
that,
I guess I
from
tried
that
to define.
perspective,
Yeah,
I
I
would
guess I
say
was trying to say.
they belong to this really high bandwidth, coherent memory domain.
To me, that's the difference, the terminology. If you're going to call it scale up, then it's got to be a memory consistent domain. And if you don't have that high level of consistency, then it's not really scale up.
Yeah, they call it ICI, right? So ICI domain is equivalent to the NVLink domain.
Mm-hmm.
And if you look at their scale out, is different because then you need an ACAR and you go to different switch architecture with much lower bandwidth. I think we can look at it more, but I think that's how Google actually claim to have much better overall system performance because they just have bigger, I don't know, they call it super pot, right? And this is again an area people are interested in scale up too, because they basically we talked about anytime you introduce a switch or packet switch, you introduce latency, right? Using OCS, you basically just doing connectivity without this extra layer of packet switching in between.
Yeah, I think this would be an interesting part. I don't the only things that I'm worried about is if we have enough resource or bandwidth.
No, that's okay, Bobby. You
Yeah.
can leave it as a later maybe revision 2 or something if you
Yeah,
think it's
yeah.
like too much. But what I'm saying, this is a relevant area for scale up.
Mm-hmm. Yep. Thanks for that. So this is pretty much all the outlines that I kind of start drafting together. So I know we're out of time right now for 10 minutes, and so what I will do is I think we should end here, and I'll send out the notes. Please, everyone, just go take a look, and if you're able to, please sign up for any small sessions or something, and help contribute the white paper. Okay, we're ended in here. Thank you all, and wish you have a very nice holiday. Bye.
Thank you. Have a nice July 4th.
Thank you. Bye.